The TLDW, this HerculeZ 2000 version of the GTX 770, required trace repair work, putting back a handful of components and even undervolting the VRAM to get it to work properly. This was an adventure filled with lessons for me. I learned about why using filtering capacitors for the internal reference voltages in phase controllers is a good idea, why doing proper compensation on phase controllers is a good idea, and so on. So, grab your favorite snack, a hot beverage and a blanket, and curl in a comfortable armchair or couch. This story is long. Like almost all my repair videos, everything started with an ad. The seller had a package deal for 10 USD, a reference board like HD 5770, and a 2-fan GTX 770 from Inno3D. Since the website was also running a promotion that month, free shipping, I figured that even if both cards stay dead, it's still worth getting the deal for the components alone. The cards arrived soon after placing the order, but the packaging... To put it this way, there was not an actual box being used. There were just 2 pieces of cardboard wrapped around the contents and held together with tape. As for the inside, the 2 cards were strapped with their PCBs facing each other and just a thin layer of foam in between and around them. Measuring the resistances between ground and various power inputs showed nothing suspicious. Measuring the resistance between ground and various auxiliary power rails provided no surprise as well. The only low resistance value, of a few ohms, was found between the inductors powering the GPU and ground, but that is typically okay for GPUs. I decided to power up the card. The fan started to spin at a high speed and I got no image. Voltage measurement showed that the VRAM was powered, the 5V supply was also working, but the GPU had only 30 mV applied to it. Visual inspection of the PCB showed, initially, just a dislodged capacitor from what was looking to be the daughter board holding the VRAM phase controller for the GPU power. Using some high-resolution pictures of similar cards with almost identical PCB design, I then took a closer look, focusing on an area of the board that had a lot of scratches. This revealed a handful of other missing components, 2 more missing capacitors on said daughter board, and 2 capacitors and a few resistors on the main PCB. Using the multimeter in continuity mode and the schematics for another GTX 770, the MSI gaming version, I was able to identify the missing components from the main board and their meaning. I was missing 2 pull-up resistors at 10K and a third resistor of 1K that was supposed to pass the NVidia power good signal. Among the missing capacitors, the board was missing a 10 nanofarads one and the C603 1 microfarad MLCC. As for the damage traces, I had to handle 2 of them, one for the 1K resistor and another one for the 10 nanofarads capacitor. For the daughter board, however, I had to resort to the datasheet of the 5-phase controller placed there, a Richtech RT8802A. Using the typical usage example schematics and the multimeter in continuity mode, I managed to find out that the missing components were a 2.2 nanofarads capacitor and a 0.1 microfarad. I started the repairs with the trace for the 1K resistor. Again, I used thin copper wire, some extra tin on the remains of the trace, and a drop of liquid flux to help me float and position the wire on the trace. It was then up to the hot air station to perform the actual soldering. I then lifted a 1K resistor from my favorite donor board, the dead GTX 960, and used the same technique. Put a drop of flux, then float the resistor in place, then heat up the entire thing. I then followed a very similar procedure to repair the trace for the 10 nanofarads cap, and then added the cap itself. The practice that I got with the Fermi GT730 certainly paid off. The 10K resistors that had their pads in a good shape were easier to do. Simply find a part with the correct value, albeit not critical for a pull-up resistor. Use a drop of flux to float it in place, then use the hot air to solder it. The daughter board with the NVidia phase controller didn't have any traces damaged, so the repair here consisted in finding the capacitors with the appropriate values and soldering them in place. Again, the GTX 960 donor board came to the rescue and provided the two capacitors. Like in the previous cases, I used flux to help me float the capacitors in place and to solder them. With all of that done, after doing a sanity check on the card for shorts, I powered it up. And I got 90 millivolts for the GPU power. I needed 10 times as much. Something was still wrong, so I took another look at the datasheet of the phase controller. I had 12 volts coming into the MOSFETs. I had 5 volts powering the RT8802A, so the next culprit as to why things didn't run would be the enable signal for the said controller. After tracing it on the board, I powered the card again and lo and behold, the signal was about 0 volts. I based my repairs on the MSI GTX 770 Gaming Edition. The printed labels on the board match the ones on the schematics. I found that there are a few transistors involved in generating the enable signal, checking the presence of various power signals. Q507 checks the 12 volts on the PCIe connector, Q53 checks for the 3.3 volts, Q48 checks for the sense connection on the 8-pin connector, Q45 does the same for the 6-pin connector. Q49 checks for the external 6-pin connector 12 volts, while Q50 does the same for the 8-pin connector. I mapped out the expected voltages on the diagram and made sure to have the annotated diagram on my phone. I then proceeded to measure the actual voltages. Not quite what I expected. I decided to take a shortcut for the time being, since I already knew that all the voltages were present on the board. So instead of fixing the power-up circuit, I took a shortcut and shorted the base of Q52 to ground. This would cause it to stay open circuit, and the enable signal would stay high. After checking if the GPU and memory still work, I'd then return to the power sequencing circuit, or at least that was the plan. And I got 900 millivolts on the GPU and about 1.6 volts for the VRAM, so I turned anxiously to the monitor, only to get a black screen. Funny enough though, the monitor was not in power savings mode, so something was being sent through the DVI-D port I was using. Frustrated, I went on to check other outputs, and lo and behold, the HDMI was providing an image all along. I went on to install the driver successfully, and at that point the DVI-D port I tried to use previously worked fine to connect a second monitor and to extend the desktop on it. However, I had to turn off the PC. The bar got really hot in the VRM area. I suspected that the 2.2 nanofarad MLCC that I soldered was having issues, and it would actually act as a much lower capacitor. This would end up with poor compensation for the shape of the PWM signals, and the MOSFETs could end up spending too much time in the linear region instead of in either on or off states. This means significantly more power had to be dissipated by the MOSFETs, heating them up even at idle. So I ended up searching for another 2.2 nanofarad MLCC. This time around the GTX 960 was spent on them. The value is not particularly common. They are usually one of them per phase controller, and I botched the one available on the 960. So I ended up searching for one on a defective motherboard. You know, the one you've seen in the R9-290X recap video. The phase controller there did have a 2.2 nanofarad MLCC, so I transferred that to the 770. And finally, the PCB remained fairly cool on the VRM area, to the point I felt comfortable even to run short gaming tests. We're still quite far from the end of the video, and I didn't mention the VRAM issues, so you know that something's about to happen. If you found this story to be keeping you on the edge of your seats, then consider dropping a like. Back to our video card. Well, it started to exhibit artifacts. I can't explain why, well, maybe because I had no other idea in my mind, but I grabbed my multimeter and started measuring voltages. It was a very long shot, but I found that the voltage for the memory was 1.7 volts, about 100 millivolts more than what I expected. Now, going through the schematics, two values for the VRAM voltages would make sense, 1.38 volts and 1.6 volts. And monitoring the voltage during boot, I found that the RAM gets first powered at 1.6 volts, then drops to 1.38 volts while the operating system loads, and at the point of loading the video driver, the voltage would shoot up to 1.7 volts. The datasheet for the memory phase controller mentions that the chip has its own internal 5 volts rail, that it is used internally, and that it can also provide power outside the chip. It also mentions that the output must use at least a 1 microfarad capacitor to provide more resilience against input variations. Could such instabilities be responsible for driving the memory rail up by 100 millivolts? Well, one way to find out. Get an MLCC and solder it in place. I had the choice between a 1 microfarad MLCC on the GTX 960, my favorite donor board, and the 10 microfarad one, which had a better placement for harvesting. I went for the 10 microfarad since the datasheet mentioned at least 1 microfarad. And the voltage now went 1.6 volts to 1.38 volts, then back to 1.6 volts as the PC booted with the card slotted in the mining adapter. And no more artifacts, not even while running Heaven, suggesting that the memory voltage can be another cause for such behavior. Well, that is until I played Warframe. This game is somewhat the Furmark equivalent for actual games, as it can heat up older cards quite a lot. After 15 minutes of play, the image changed color a bit, then threw a few artifacts. To complicate things a bit, just before artefacting, I was running Heaven, and I noticed a behavior related to the power draw that did not look right to me, in terms of how the power was being drawn. It caused me to use my multimeter in continuity mode, and I traced 2 phases being powered by the 6-pin connector, and the other 3 powered by the 8-pin. Now, considering that all 5 phases would have equal loads, the power draw would be a 60-40 split between the 8-pin and 6-pin connectors. What I saw was not a 60-40 split. The 3 phases powered by the 8-pin connectors bore the brunt of the power requirements, while the 2 phases powered from the 6-pin connector were significantly less loaded. And now, besides what seemed to me like a lack of load balancing, the card was also exhibiting artifacts. I stopped investigating the load balance issue and decided to investigate the artefacting behavior. I checked again the memory voltage rail, and this time around it was fine. With a lack of leads to go on, I switched back to 2 older issues that the card had, the power sequencing circuit and the phase load balance. For the power balancing issue, I tried to detect any differences in circuitry between the phases powered by the external 6-pin connector and the ones powered by the 8-pin. I found that for one of the phases, I named it Q38 after the label of the high-side MOSFET, what was supposed to be a 2.2 ohm resistor measured in actuality 4 ohms. And funny enough, Q38 was getting its 12 volt input from the 6-pin connector. Could this be it? Could it be that replacing that resistor would get us the 60-40 split between the load? Nope. Sorry for the suspense. I pretty much experimented with finding a fix for the artefacting issue. At some point I noticed that the plate that served as heatsink for the memory chips and MOSFETs was not making proper contact to one of the memory chips due to a missing screw. And adding that screw got the card working to the point that it ran Warframe, the Firmac equivalent but for actual games, and the card exhibited no issues. I then threw all the games that I use as benchmark at it, and it ran fine, to the point that I managed to put up a review for the card on the other channel, a link for both channel and video in the description. Then the card decided to artifact again, this time in desktop at idle. Now, for the moment I was out of ideas, and with the review done I decided to give the GTX 770 a rest, with a promise to come back to it to fix the artefacting and the power sequence circuit. Time passed, the DDR4 GT 1030 got fixed, then the Radeon HD 5770 that came with the 770 also got fixed. And the fix for the Radeon's power sequence circuit got me suspecting that the GTX 770 had a similar issue with its own power sequence circuit. And lo and behold, using the multimeter in continuity mode, I found the base of Q50 connected to one pad from a suspicious looking pair of pads. And the other pad from the pair? Why, yes, it was connected to the 12 volts from the 8-pin PCI connector. As for the 7.5K resistor, well, how about no resistor at all? I removed an 8K resistor from the Lenovo IH61M motherboard and placed it where it was supposed to be R558. This got the power sequence circuit to work as intended. No need to short the base of Q52 to the ground. As for the artifacting issue, I pinned it to silicon degradation, not to a completely defected memory chip. To alleviate it, I decided to put the memory in a less demanding operating point. And since I could not reduce the frequency, I decided to reduce the voltage that the chips operate at. You see, according to the schematics, the chips can work as low as 1.38 volts as long as the frequency is reduced as well. And this happens at idle. In load, the frequency would increase, and so would the voltage up to 1.6 volts. My plan was to lower this in-load voltage from 1.6 volts to 1.55 volts or similar. This would require increasing the value of R134 from 14K to about 17K. Unfortunately, I could not locate any 17K resistor on my donor boards. However, I could find 22K resistors on the same Lenovo motherboard in the audio jacks area. This, however, would reduce the memory voltage further to a value of 1.53 volts, or about 70 millivolts lower than the nominal value. Would that be enough to help with the artifacts? Would it be too much and end up introducing instabilities during load? Only one way to find out. In the same soldering session in which I added the missing R558, I removed the existing 14K resistor for R134. I then lifted the 22K resistors from the Lenovo motherboard and placed it in its place. I added in a proper reassemble of the card and powered it up. As already mentioned, the now populated pads for the R558 did their job, and the card powered up fine. GPU voltage was good, and the memory voltage was the expected lower value of 1.53 volts. And the desktop was looking fine. But how about heaven? This would put a bit of load on it. Will it be enough to artifact? No, apparently no. No artifacting. So yeah, the card seems to be working just fine now. I pretty much experimented with finding a fix for the artifacting issue. At some point I noticed that the plate that served as heating I then followed a very similar procedure to replace the trays for the